All right, let's get started. Good afternoon, everyone. Last time we talked about chapter 2, which is probability. We give the basic idea of what is probability and what are the counting techniques, such as permutation and combination, and under what circumstances we use combination or permutation. Okay, and also we discussed conditional probability. Okay, so today let's continue. Okay, so last time I stopped here. Law of total probability. Okay, so in this case, we have A1, A2, A3, A4, AN, and this N cases are mutually exclusive and also exhaustive. Okay, so which means A1 and A2, sorry, A1 and A2 will equal to empty space. So there's nothing in common between A1 and A2, and also A2 and A3. Okay, so A1, A2, A3, and AN. Okay, so they have nothing in common. The intersection is empty space. Okay, so they call it exclusive.
I don't see an app for that. You'll need to download one.
No. Also, they are exhaustive. So exhaustive means the addition of A1, A2, AN will including everything. Okay. So A1, A2, A3, AN. So they will include sample space. Okay, the half circle facing up is all. Okay, so this means the event A1, AN are mutually exclusive and also exhaustive. And event B is any event. Okay, like we can see from here, any event in that circle B. And then PB is equal to PA1, this is and B, plus PA2 and B, plus, okay, PAN and B. Okay, so seeing from the Venn diagram, we call this diagram Venn diagram. Okay, so A1 and B is this shaded area. Okay, so this is A1 and B. And this area will be A2 and B. Okay, A2 and B. Okay, so the property of A1 and B plus the property of A2 and B plus blah blah plus the last one PAN and B. Okay, so this will be all these pieces added together. So that's equal to PB. Right. So PB is equal to PA1 and B plus PB, PA2 and B plus PAN and B. All right, so that is equation for total probability. All right. Another equation for that is here. Okay, if PAI is not equal to 0, and then PB can be rewrite as this equation. Okay.
Quick question.
Sure.
The L means dot, 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 right?
Yeah. Sorry. As always, the L means dot, dot, dot.
Okay.
Dot, dot, dot. Okay.
Okay.
Okay. So these two equation is the same because this part is equal to this part. And that part is equal to that part, which we discussed last week. Okay, so last week we talked about conditional property. Okay, for example, PB given A1 is equal to PB and A1 over PA1. Okay, so that will translate into PB and A1 equal to PB given A1 times PA1. All right. Okay. So that's why this part PA1 and PB is equal to that part. All right. Okay. So this is the equation for total probability when A1, A2, and AN are mutually exclusive and exhaustive events. Okay. Then let's look at the example. Okay.
I'm sorry, what is that vertical line in the parentheses in between the B and the A? What does that represent again?
Given. Condition.
Given. Okay.
Given,
I see.
yeah. PB given A1, which means given A1 is happened already. What is probability of B? So this is PB given A1. Okay. Or in other words, the probability of B under the condition of A1 already happens. Okay. So seeing from the Venn diagram, okay, so PB is this circle, right? Given A1 is happened is under this area of A1. Okay. All right. Again, that is conditional probability. The line, vertical line means given. All right. So example, customer bought a certain make of car, can order an engine in any three sizes. Okay. So of all the cars sold, 45% have smallest engine, and 35% has medium-sized engine, and the remaining 20% has the largest engine. Okay, so then let's say the engine size, small, medium, and large are exhaustive and exclusive events, which means they have nothing in common. So the engine is small, cannot be also be large or medium. Okay, so they are exclusive, and also they are exhaustive because we only have three engine size. You have to pick one of the three: small, medium, or large, no more. So 45% plus 35 plus 20 is equal to 100%. Okay, again, engine size are exhaustive and exclusive events. Sorry. Of cars with the smallest engine, 10% fail emission tests within 2 years. Okay. 12% with medium engine size, and 15 of those with largest engine size fail within 2 years. Okay. So the question is asking what is probability that a randomly chosen car will fail emission tests within 2 years. Okay, so we're gonna use the equation for total probability. Okay, so let's draw a Venn diagram. Okay, so let's see small engine, that's 45%. Medium engine, 35%. Okay. And large engine, 20%. Okay. And again, the three engine size are exclusive and exclusive events. Okay. And then let's define fail the emission test within 2 years as this circle. Okay. And this is failed engine emission test. Okay. So the probability engine fail based on the equation of total probability will be probability of the engine fail when the engine size is small. Okay. Plus probability engine fail and engine size is medium. Plus the probability the engine fail when the engine size is large. Okay, so see from the Venn diagram, the first part, probability to fail when the engine size is small, is this shaded area. Okay, and probabilities fail when the engine size is small, is medium, is this area, and so on. Okay. The first part is equal to the probability the engine size is small times engine fail given the engine size is small. Okay, and both of these two is given by the question. Okay, so 45% of the engine is small, so that's 0.45 times the probability the engine fail when the engine size is small. Okay, that is 10%, 0.1. Okay, so similarly for the second part, it is equal to 0.35, which is the probability it is medium size engine, times 0.12. When the engine size is medium, 12% will fail. All right, and last part is 0.2, which is percentage of large engine times 0.15, which is the probability the engine will fail when the engine size is large. Okay, that is one example of total probability. So the condition for that is the events are exclusive and exclusive. Okay, in this case, engine size are exclusive and exclusive. Okay, so that's the two basic conditions before we can use the law of total probability. All right. Any questions before we continue? All right.
I have a question.
Sure.
So for the last part, the equation, I got a little confused. Like you circled that one part fail small, the probability, and then you said it equals to probability of small times probability of fail in small,
Yes.
and
yes.
then it equals that like the 0.45 times 0.1 and then
Yes.
plus 0.3 point. Yeah, is that like for like the small, medium, and large, or
Yes. So this
okay?
part,
Because
this is the first part here. Okay. And 0.35
okay,
and 0.12 is the second part. And this part is this part.
okay, just making sure.
Yeah, okay. Yeah, that is because, we have, for the equation, we have two format. Okay, this part, PA1 and B is equal to PB given A1 times PA1. Okay, so whatever the question give us, we can use whichever equation. Okay, in our equation, our example, the equation, we should use this equation because the question tells us this information. Okay.
Right.
Yeah. And seeing from the Venn diagram, we can see more clearly what does that mean. Okay. So P fail and small is actually the shaded area here. Okay. And so on.
What's the diagram called again? Sorry.
Venn diagram here. I write it down. Okay. WAYNE. Yeah.
Oh, Wayne diagram.
Yeah, Venn diagram.
Thank you.
Okay. Yeah, for probability, conditional probability, quite often it's helpful to draw the Venn diagram to help us understand what the question is asking. Okay.
Right. Okay.
Okay, so let's continue. Multiplicative rule for intersection. Okay, so if events A and B are independent, and then we know from last week, the probability that both A and B occurs is PB and PA and B, half circle facing down is and, okay, is equal to PA times PB. Okay. All right, look at another example. In certain population, 10% people can be classified as being high risk for heart attack. Okay. So 3% randomly chosen from population. What is probability that exactly one of the three are high risk? Okay. So we pick 3% from a whole population. And these three picks are independent. Okay. So pick 1, pick 2, and pick 3 are independent to each other. All right. So the question is asking the probability exactly one has high risk. Okay. So could happen in 3 scenarios, depending on the result of the 3 picks. Could be the first pick is H, H means high. The second and the third are not high, okay? So P, H, and N. When we define H as high risk and N is not high risk. Or the high risk could happen in the second peak here. But the first and third peak are not high risk. Or the high risk could happen in the third peak, but not on the first 2 peaks. Okay, and because these 3 peaks are independent, so PH and N is equal to PH times PN times PN. Okay, so the probability has high risk, so that is 10%, 0.1, because 10% of the people can be high risk. And same, the probability we pick non-high risk people is 90%, so 0.9. Okay, so we plug in the equation and we get the answer. So 25% of the chance exactly one of the 3 are high risk. So let's say we have more information about the previous example. We know that only 49% of population are female. Okay, and of female patient, 8% high risk. Right. A single person is selected and random questions asking the probability that it is high risk female. Okay, so first of all, we define H, high risk. F means female. Okay, and the question tells us the probability it is a female is 49%. Also tells us when it is female, the probability she has high risk is 8%. Okay, so use the multiplicative rule. The probability is high risk female is equal to the probability is high risk and it is female, which is again equal to the probability is female times the probability is high risk given, again this is given, it is female, okay, which is 49% times 8%. So we have 3.92%. A single person picked is a high risk female. All right. Next, let's discuss a so-called Bayes rule. Okay. And before we know PA given B, this is given, is equal to PA and B times over PB. Okay. Again, seen from the Venn diagram. Let's see, this is A, this is B. Okay. And this part will be A and B, right? And PB is the whole circle. This is B. The whole circle is B. It's PB. It's B. Okay, so PA given B will be basically this part, the intersection of A and B over the circle of B. Okay. So Bayes' rule tells us when we have n events, A1, A2, An, which again mutually exclusive and exclusive. Right. And for each AI is not equal to 0, and PB is any event which is non-zero, then okay, so this equation holds true. So PAK given B is equal to PB given AK times PAK and over this part. All right. Okay, again, use Venn diagram. We see what does this equation tells us? What does this equation mean? Okay. Let me draw this. Okay. Again, let's draw a Venn diagram. In this case, we have A1, A2, AK are mutually exclusive and exclusive events. So let's say this is A1, A2, A3, and AK, AN. All right. So these n events A are mutually exclusive, which means they have no intersection, and exclusive, which means A1 plus A2 plus A3 plus AN, they are the sample space, including everything. All right. And then let's draw B. Okay, let's say B is here. All right, so this is circle B. And this is AK. All right. So PAK given B means what? Means the probability is within this AK piece. AK is here. Given B means it within the circle of B. Okay, so that probability is equal to PB given AK times PAK. And this part is equal to PB and AK. Okay, and PB and AK is this shaded area. Okay, and then let's look at this part, which is the sum of PB given AI times PAI. Okay, so what does this mean? So that basically means every piece of shaded area added together, okay, which is equal to P, B, and A1 plus PB and A2 plus blah blah plus PB and AN. Okay, and PB and A1 is here, right? This part. Okay, so Bayes' rule just tells us probability AK given B is equal to PB and AK, these areas, over the whole circle of B. The whole circle of B is this part. All right. So using Bayes' rule, let's resolve another question. Okay, so that's the previous question about heart attack. Okay, so from the previous example, we know 49% are female, and for female, 8% high risk for heart attack, and for male patient, 12% are high risk. Okay, a single person is selected at random and found to be high risk. Okay, so what is probability that it is a male? Okay, so first of all, let's figure out what is the question asking. Okay, the question tells us the person chosen is already high risk. Okay, so that is conditional probability. So given it is high risk, what is probability it is male? So that is PM given H. Probability it is male given it has high risk already. Okay, so using Bayes' rule, okay, we can using this equation. That is PM, the probability is male, times PH given M, the probability has high risk given it is male, okay, over PM times PH given M plus PF times PH given F. This is F means female, PH given F means high risk given female. Okay, and all this information is already given from the question. Okay, again, you can use this Venn diagram to help you understand. Okay, let's look at another example. Okay, we can draw the diagram again, and using the equation, the Bayes equation. Right. The proportion of people in a given community has a certain disease is 0.005. Okay. A test is available to diagnose the disease. If a person has a disease, the probability the test will produce a positive signal is 99%. Okay. If a person does not have the disease, the probability that test will produce a positive, which is a false positive, right, is 1%. Okay. So if a person tests positive, the question is asking, what is probably that person actually has the disease? Okay. All right. So in this question, we have two exclusive and exclusive events. Okay. So one is the person has no disease. Okay. So no disease. (99.5%). Okay. And the other part is, let's see, has disease, which is 0.005, right? So 1 minus 0.995 is 0.0005. Okay. So let's say the circle represent the test is positive. So let's say that circle means the test gave a positive result. Okay. So the question is asking, given a person tests positive, which means it within the circle of positive within that small circle, what is probability that person actually has the disease? Okay. So basically means this shaded area, okay, that is the probability it has disease and test positive, okay, over the areas of the whole circle, the circle of test positive. All right. So based on that, we can figure out, okay. Let's see the next slides. So that define D is a person actually has a disease, and plus means test give a positive signal. Okay, positive signal. And this is what we know. 0.5% person has a disease. If the person has a disease, the test is positive is 99%. If the person does not have a disease, this is DC means complement of D, means does not have a disease, no disease. So that's the condition. So this part means the probability the test gave a positive given the person has no disease, 1%. The question told us. So using the Bayes rule or the Venn diagram I just showed us, okay. So PD given positive, okay, is equal to P positive given the person has a disease times PD, the person has a disease. Okay, so this part is equal to that small shaded area, and this part plus that part, okay, is again the whole circle of positive. Okay, so that part added together is the positive circle. So that area. Okay. And we add each part together and plug in the information. So we get the property the person has disease. If we know the test give a positive, will be 33.2%. Okay, all right. Okay, so I know the concept is could be very confusing at the beginning. Okay. So trying to review what we learned today and using the Venn diagram, trying to see which part means what. Okay, and the Venn diagram may help you understand the whole situation, the whole meaning of this given probability, conditional probability. Okay. All right. So section 2.2 and 2.3, I will see maybe one of the most complicated part for this class. Okay. If you take time for many of us to digest and fully understand, the whole concept. Okay. So don't get frustrated if at the beginning you don't know what I'm talking about. Okay. All right. Section 2.4, which will be much easier, but this is a new information. Random variables. But before we continue, any questions about section 2.3? See, we have many chats. Okay. All right. Random variables, okay, assign numerical value to each outcome of the experiment. Okay. So if, for example, we toss a coin, we can define the coin, then the tail, we can give a number 0. Okay. Or the coin, then the head, we can see we assign number of equal to 1. Okay. So we have two possible outcomes, tail and head. So 0 and 1. So we can assign numerical value to random variables. This is some other examples. SAT score, okay, number of people in the room, number of cars, intersection, compressive strength of concrete. Then we're gonna give a unit, for example, megapascal. Precipitation intensity on given hours, okay, how much rain per hour. Okay, so yesterday we have a flood warning. Okay, so millimeter per hour, or the mode of transportation selected by a person. Okay, so that could be by feet, by bus, right, by car, bike, and so on. Okay, and then we can assign some value for that. For example, 1 by feet, 2 by bars, 3 and 4, for different modes. Okay. So going back to our old problems, okay, so a set of 6 resistors, and they are labeled 10 ohms, and 3 labeled 10 ohms, and the other 3 labeled 20 ohms. Okay, I think we discussed that problems last week. The engineer will connect 10 ohm resistors with 20 ohm resistors. Okay, and for the 3 resistors labeled 10 ohms, actually this is 9, 10, 11, and the 3 labeled 20 actually is 19, 20, and 21 ohms. Right? Okay, so we discussed that problems before. Okay, so the process of selecting one resistors from each of the 10 ohm box and 20 ohm box. So that's the experiment. Okay. And the sample space again is defined as all the possible outcomes. Okay, so the sample space consists of 9 equally likely outcomes. How come? So using what we learned last week, the counting method. Okay, so let's see the first step. We select one from the box with 10 ohms. Okay, then could be 9, 10, or 11. Okay, and then we pick another one from the second box. Okay, for 9, we could have 10, 9, 10, 11. No, 19, 20, and 21. Okay. If the first pick is 10, we could also be 19, 20, and 21. And same thing for the first pick is 11. All right. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 possible outcomes. So this is how we have the table like this. Okay. So the outcome will be 9, 19, 9, 20, 9, 21, and so on. Okay. And here is probability. So every one of these 9 outcomes, the probability is the same, 1 over 9. Okay. And then let's add the ohms together. Okay. So 9 plus 29 equal to 28. 9 plus 20 equal to 29, and so on. Okay. And we also notice some of these total ohms resistance are the same. For example, for 30 we have here, here, and here. We have 3 30s. Right. Right. And then we're gonna add the probability for each total ohms together. Okay. For example, for 30, it's gonna be 1 over 9 plus 1 over 9 plus 1 over 9. For 28, so 28 only occurs once, so that is 1 over 9, and so on. Okay, so far it's very straightforward. Okay, so here. So after the summary little calculation, this table contains all the information we need. Here, this table. To complete any probability regarding the random variable x. Again, the x is defined as the total ohms of these 2 peaks. Okay, so the possible outcomes will be 28, 29, 30, 31, and 32. And we call that sample space, right? Sample space. So sample space has 5 possible outcomes. And for each possible outcomes, here shows the probability. So Px equal to x. So Px equal to 28, the probability is 1 over 9. Okay. And also, we're gonna make sure all the probability added together will equal to 1. Okay, so it has to be equal to 1. Okay, otherwise something is wrong. And the random variables can be discrete or continuous. Okay, today we just discussed discrete random variables. Okay. Thursday we'll continue talk about continuous variables. Random variables is discrete if its possible values are a discrete set. like the total ohms, 28, 29, 30, 31. So they are not continuous. So they are discrete set. So that means if the possible values are arranged in an order, that will be a gap between each value and the next one. So that's a gap between 28 and 29, and between 29 and 30. Okay. And the set of possible values may be infinite or maybe finite for our previous example. Okay. Here is another example. Okay. So number of flaws in a 1-inch length of copper wire vary from wire to wire. Overall, 48% of the wire produce no flaw, 39% has 1 flaw, and 12% has 2 flaws, and 1% has 3 flaws. Okay. So let's define X is number of flaws in a randomly chosen piece of wire. Okay. So Px equal to 0 means the probability the flaw is equal to 0 is 48% based on the question. Ps equal to 1, 39%. 12% for Px equal to 2, and 1% for Px equal to 3. Okay, so this lists all the possible values. Okay, so number of flaw only has 1, 2, 3, 4 possible values, which means which including 0 flaw, 1, 2, or 3. And all the probability added together, you can check, is equal to 100%. So this will provide a complete description of the population for the number of flaw. Okay, and we have special name, special definition for that. But this is called probability mass function. Okay, probability mass function. The description of the possible values of X and the probability for each has a name, probability mass function, or PMF. Okay, so this is for discrete variables. For continuous variables, that name will be changed. It's called probability density function, or PDF. Okay, so PMF, or probability mass function, is for discrete random variables. So we can write Px equal to Px equal to X. So this is the possible values. For example, 0, flaw, 1, 2, or 3 flaws. Px equal to X, the X in the capital letter is the random variables. Okay, for example, the number of flaw. Okay, that's another name for probability mass function. It is called probability distribution. Okay. So far, the idea in this session is pretty straightforward. So for discrete variables, let's look at another old example. Okay, we toss a coin 3 times. Okay, and if we define number of heads as X, okay, and then using counting method, okay, 3 steps. The first step, we could have head or tail. The second step, the second choice, we also have head or tail, and so does the third one. So 2 times 2 times 2 equal to 8. So we have 8 possible outcomes, as we can see from here. Okay, and for each of these outcomes, we have equally likely possibility, so 1 over 8. So because x is defined as the number of heads, so let's just count the number of heads for each of these outcomes. Okay, the first one, H, so we have 3 heads. So 3 heads, the x is equal to 3. Okay. The second one, H, tail, so we have 2 heads, so x is 2, and so on. And we can also see for 2 heads we have here, here, and here. So we have 3 outcomes which has 2 heads. Okay, then we should edit the probability. So 1 over 8 times 3. So it means the probability it has 2 heads is equal to 3 over 8. Okay. So in summary, first of all, we list all the possible outcomes. So what are the possible outcomes? So we could have 0 heads. The probability of 0 heads is 1 over 8. We could have 1 head, 3 over 8 probability. 2 heads, 3 over 8. And 3 heads, 1 over 8. Okay, and we should also check if we added the px together, the sum is it equal to 1? Okay, it must be equal to 1. So in this case, it is equal to 100%. Yeah. And then we can draw a so-called histogram, okay, based on the number of possible outcomes. For the x-axis, for the y-axis is the probability. Okay. We're gonna talk about that in a moment. The histogram. So the property mass function for that example of number of floors in a where, okay. So for the number of floor, we could have 0, 1, 2, or 3. Okay. For the height, y-axis, that is probability. Okay. For example, the probability has 0 floor is 48%. Okay, 48%. So that is probability mass function. It gives us the full description of what are the probability for each one of all the possible outcomes. Okay. So the next part, we have a new name, is called cumulative distribution function. Okay, so cumulative distribution function is calculated based on probability mass function. Okay, probability mass function gives us the probability that random variables is equal to a given value, like we just discussed. The cumulative distribution function, or CDF, specifies the probability that a random variable is less than or equal to a given value. Okay, so basically we just add the probability, all the probability for the variables less than or equal to a given value. Right. And the cumulative distribution function can be read as fx equal to p for x less or equal to a certain value. Go back to the number of floor in a where example. Okay, so let's figure out what is cumulative function. So property mass function given us, the property has 0 floor is 48%, property has 1 floor 39%, 2 floor 12%, 3 floor 1%. Okay, so this is mass function. If we want to calculate the cumulative function, F0 means the property, the number of floor is less or equal to 0. Okay, which is equal to 48% based on PMF. Okay, 48%. For the number of floor less or equal to 1%, so F1, which means the property number of floor less or equal to 1, that is equal to 48% plus 39%. So that's including the probability number of floor equal to 0 plus the probability number of floor equal to 1, which is here. Okay, so 0.87%. So on, we can also calculate the cumulative function F2, which is probability for number of floor equal to 0, equal to 1, and equal to 2. So 0.48 plus 0.39 plus 0.12. Okay. And F3, the property, the number of floor less or equal to 3, will be all the 4 probability added together. That is equal to 100%. Okay. So again, we can see cumulative discrete function specify the property the random variables is less than or equal to a given value. Less than or equal to a given value. Okay. How to calculate is very simple. We just add the probability for all the possible x less or equal to a certain value. Okay. Like we can see from here. So based on this, we can also draw the cumulative distribution function. So the XL is the number of floor. Okay, the YXL is the probability or the cumulative distribution function. Okay, for example, the probability it has less than 0 floor, doesn't have any physical meaning, but that will equal to 0. Okay, so the probability it has less or equal to 1 floor is equal to 48%. Less than 1 floor. Okay, and so on. And the probability has for F larger than 4, that value will be 100%, as you can see here. So in summary, in this section 2.4, we discuss discrete random variables. The concept is very simple, as you can see here. So nothing too complicated. So we discuss what is PMF. Okay, PMF is Px is equal to Px equal to x. We also know how to calculate the cumulative distribution function, which is the probability for the value less or equal to x added together. So the sum is over all possible values of x. And then let's look at how to calculate the mean value and variance for discrete random variables. Okay. So if we have discrete random variables px equal to px equal to x, okay, so this is the PMF. The mean value will be the sum of x times px equal to x. Okay, so this small x is the possible values. For example, the number of floor. Okay, and that part is the probability for that possible values. For example, the number of floor equal to 0 is 48%. So that's the p-value. Okay, the mean value is calculated based on this, the sum of x times px. We can also call the mean value as expectation or expected values, or we can write as mu or ex. So they are the same thing. Okay, so remember this question. The variance for discrete random variables, okay, can be either calculated using either of these two equations. All right. Okay. From early lecture, we know we have equations for sigma, right, from the population. Or mean value. Okay, so the format of the variance is very similar to this. Okay, it's just x minus mu x times px. Okay, let me write down another format for that. The mean value. Okay. So again, here the p value is the probability. So the variance can also be read as Vx or sigma square. Okay. And the standard deviation is the square root of the variance. Okay. The square root of the variance is this. Okay, so when we have the property mass function, we can easily calculate the mean value and the variance based on the equation in these slides and the previous slides. Okay. Then let's do an example here. So this is the question: toss a coin 3 times, number of heads. Okay, so all the possible values is here, 0, 1, 2, 3. Okay. Px is the probability for that all comes. Okay. So based on the equation of the mean value, so the mean value is the sum of x times px. Okay. So for example, x 0 times px 1 over 8. Okay. This is x times px. So the other one, 1 times 3/8, that's 3/8. So sum of them, the mean value is 1.5. And also we can easily calculate the variance, sigma square. okay, based on this equation. Okay. So after calculation, we found out the variance is 0.75 and the standard deviation, which is the square root of variance, is 0.688. All right. So here is another example. Let's do it together. So a certain industry process is brought down for recalibration whenever the quality of items produced fall below specs. X is number of times the process is recalibrated during a week, and X has the following probability mass function. So the probability mass function is given. Based on the PMF, we can easily calculate the mean value. Okay, so let's just list the equation. Right. So from the mean and the variance, the mean value mu x is equal to the sum of x times px equal to small x. Okay, so x is here, so px is here, the second row. So x times px will be here. Let's say 0 times 0.35, 0. Okay, 1 times 0.25, 0.25. This is 0.4, 0.45, 0.2. Okay, so then that will be 0 plus 0.25, 0.4, here, 45, 2. Okay, so that is equal to 1.3. So that's the mean value. Okay, so very, very straightforward. For the variance sigma square, we can use one of two equations. So let's use this. X minus mu, which we just calculated, square times px. Okay, so let's just plug in the number. For the first x, 0. Okay, 0 minus mu is 1.3. 1.3 square times px is 0.35. Okay, so let's do the second one. The second x is 1 here, so 1 minus 1.3 square times px here, 0.25, and so on. All right. Okay, so very, very easy. Okay, so follow the equation. As long as we have the PMF, the probability mass function, we can easily calculate the mean value and the variance. Okay. Then let's learn how to draw the histogram. So when the possible value of discrete random variables are evenly spaced, okay, the PMF can be represented by a histogram. Okay, and the areas of rectangular center at the value x is equal to the probability px. Okay, and that histogram is called probability histogram. Okay, for example, like this. Like here. Okay, so for the possible x, 0, 1, 2, and 3, the y-axis is the probability, the px. The height of rectangular is the probability. So here is 0.48. And here is 0.39. Okay, So again, when we have the PMF, we can easily draw a property histogram. And based on the property histogram, we can get the information such as the shape of the distribution. If it's metric, it's skewed to the left or right, like in this example. Or if there's any outliers, okay, outliers again is values much larger or much smaller than typical values. And also the center and the spread. Okay, the center is judged by the mean value, mu. Okay, and the spread is specified as sigma. Okay, so the larger the spread, the larger sigma. Smaller the spread, the sigma will be smaller. So based on histogram, we can easily see this type of information. Okay, and here is the last example. Again,
Excuse me.
yes, sure.
There is a question in the chat, if you can see that. I think it was for the histograms.
Let me see.
Do you see the chat?
Yes, let me see.
Oh, for the variance calculation.
For the variance calculation. Okay.
Yeah.
Yeah, the variance can be used in can use one of these two equations. Yeah, the display will be a little bit delayed here. All right, so using one of these two equations to calculate the variance. Okay, x is the possible value of the outcome. The mu x is the mean value, and the px is the probability for x equal to that outcome. Okay, and sum of them. Okay, this is for discrete random variable. Okay. Yeah.
I don't know if that answered Kira's question for the example for variance. Sorry. Was it the, which one was it, Kira? The example 15?
Why did he choose x equal to 0 and x1 for the variance?
Next example.
X equal to 0.
I don't know which example you're referring to, Kira.
Okay, maybe you can ask me after the class, Kira. Okay, yeah, sorry. I think that's the time. We have one more slice. We just draw the histogram based on the px. Again, that is very straightforward. So the possible values. Okay, so 0, 1, 2, 3, and 4 are the possible values, and the height will be the probability. Okay, and so on. Okay, so as long as we have the probability max function, we can draw the histogram. All right, so let's stop here for the lecture. If you have questions, please stay here, and we can discuss in details about your question. Okay, thank you.